In this lecture, we're going to talk about resonance structures. And what we're really doing at this point now is we're taking our foundation we just created, which is Lewis bonding theory. And it's not perfect. It's a good bookkeeping method, but it doesn't really accurately describe bonding. And what we're going to start doing is adding layers to it and then modifying it and presenting new theories after this that get us closer and closer to an idea of bonding. And each thing will bring its own important piece to the whole picture. And so now this is going to be about kind of a modification to this idea of Lewis dot structures and how they represent molecules. So in Lewis theory, electrons are localized between the atoms that are bonding together. And to some degree, this makes sense because they're attracted to those two nuclei. So they'll spend more time in between the two nuclei. But some degree of what we call delocalization of electrons, let me highlight that. It's an awesome word, can actually stabilize the molecule. And what delocalization means is to be spread out, to not be pinned to one spot, rather than just in between the two atoms. So we see that resonance structures come in handy when there's more than one Lewis structure for a molecule that is reasonable, but differs only based in the position of the electrons. And so these are called resonance structures. They are Lewis dot structures that both represent the same molecule, and they're slightly different, but they look very similar. And the difference is where the electrons are placed. That means that the way the atoms are connected together is the same, or the order that they're connected. I call it connectivity. So that's like a way of saying, like, if I have oxygen bonded to carbon bonded to oxygen, my resonance structures will have this same pattern of oxygen, carbon, oxygen. Like that won't change. Another way of thinking about it is if I stripped my resonance structures of all the lone pairs and multiple bonds, they would look exactly the same if you were just looking at the way the single bonds connect the atoms together in space. Now, the actual molecule, like if you were to study it using different instruments, you would see, you would build a picture. You wouldn't actually see it. That the actual structure of the atom would be a hybrid, kind of a average of all of the different resonance structures that we created to describe it. And we call that a resonance hybrid. So a resonance a structure will have multiple resonance structures that combine to form a resonance hybrid. We typically see these resonance structures with molecules that have multiple bonds and lone pairs. That rearranging of electrons so the connectivity is the same really requires lone pairs and multiple bonds to work with. Here's an example. It's ozone. So ozone is 3 oxygen atoms bonded together, oxygen, oxygen, oxygen. And we can draw 2 resonance structures to describe it. So each of these are resonance structures of O3. You notice that each one has an oxygen in the middle that's bonded to 2 oxygen, and then 2 oxygen on the outside of the molecule that's only bonded to 1 oxygen. And that's the same. If I strip away all the multiple bonds and all the lone pairs, these would look exactly the same. The foundation of this is an oxygen bonded to oxygen bonded to oxygen. So that connectivity doesn't change between these two structures. What does change is the placement of that double bond. So note that the double bond is between the 2 leftmost oxygens in one structure and between the 2 rightmost in the other structure. The other thing that changes then is the lone pairs, right? So we still need to satisfy our octet rule at the end of the day. Like we need to build reasonable Lewis structures. Like that requirement hasn't left just because we're doing resonance structures. And so here I've got the 3rd lone pair on the oxygen to the left, and here it's on the right. And so it's like the lone pair switch sides and the double bond switch sides. It also looks like, and this is the part that gets really confusing, that you just flipped the molecule, right? Like it looks like the mirror image. It looks like I just put a mirror right here, and then we are looking at the mirror image of it. And that is something that can be a real struggle with thinking about resonance structures. Whenever you look at them, a lot of times it looks like you could just rotate it or flip it, and then it's exactly the same. So remember that when we're in a chemistry lab, we've got a lot of interesting tools at our disposal, and one of them is isotopically labeling elements. I could come in and make, so most of these, let's say, are oxygen 16. I can make one oxygen, let's see, 18, right? And I'll label just this one. And I'll be able to see the difference in the bond length between the oxygen 18 atom and the oxygen it's next to. And so I can label these so I can differentiate between these oxygen atoms and make sure that this like represents like reality. So if I did that, I would see then one have a short bond and then the oxygen 16 have a long bond if I'm looking at this one right here. If I'm looking at the other resonance structure, I would see a long bond to the oxygen 18 and a short bond between the two oxygen 16s. So that's how we kind of learn about this in the lab. Rather, it's not just making it up. But when we look at these, we don't see these two structures. We don't see a double bond and a single bond. Instead, what we see is two bonds that are the same length. We see a bond length of that's like 1.5 bonds, right? And bond length, if I haven't explicitly said this yet, gets shorter the more electrons are shared. The more electrons that are attracted to the two nuclei, they bring them closer together. So a single bond is longer than a double bond, which is longer than a triple bond. But we can have bond lengths that vary in between those kind of rigid assignments. We can have things that are like 1.5 bond. And that's what we see when we study ozone with isotopic labeling. We see that it actually has the same bond length between all of the oxygens, and it's longer than a double bond, but it's shorter than a single bond, which means that really we're taking these resonance structures right here and building that hybrid structure, and the hybrid resonance structure best represents how the molecule actually looks in nature.